On the evening of January 8, 2025, seismic activity across the globe presented a dynamic and complex picture. A magnitude 3.4 earthquake was recorded near Greece, highlighted by the green marker on the earthquake 3D globe. Meanwhile, California began showing signs of increased seismic activity with a notable uptick in tremors and minor quakes. Could this heightened movement along the San Andreas Fault be a precursor to something far more significant? At the same time, activity along the Cascadia Subduction zone raises a chilling question. Is this restless region hinting at a long-anticipated megathrust earthquake? Interestingly, Texas also experienced larger movements, underscoring the widespread seismic shifts. Are these tremors part of a global pattern, or do they signal localized stress building in Earth's tectonic plates? Focusing on the West Coast, Southern California remained active with a 3.0 magnitude earthquake near the creeping segment of the San Andreas Fault. This minor cluster of activity, while not alarming in isolation, adds to a larger narrative of strain accumulating in the region. Combined with ongoing wildfires in the Los Angeles area, some of which have sparked under suspicious circumstances, the potential for a catastrophic combination of disasters looms over the state. Historically, disasters often occur in sequences, and the convergence of fire and seismic activity is a troubling possibility. Farther south, the Imperial Fault experienced minor tremors, while Northern California showed modest activity near Lake Allmanor with early morning earthquakes ranging in magnitude from 2.0 to 3.0. This pattern of activity hints at elevated tectonic strain across the West Coast, spreading inland and manifesting in various seismic hotspots. In the Cascadia Subduction zone, a magnitude 2.7 earthquake occurred near the southern plate boundary. Analysis of the region's tremor map revealed 68 tremor epicenters concentrated deep beneath Northern California between 35 and 45 kilometers below the surface. This subduction activity reflects a buildup of strain along the plate interface. Historically, tremor clusters in Cascadia are often precursors to increased seismic activity nearby, a pattern observed in the region today. Seismic activity has been unusually active in several regions, raising questions about underreporting and the dynamics behind the tremors. In Northern California, seismic stations at Petrolia and Dinsmore have detected multiple tremors throughout the day, yet only one earthquake has been officially reported. The Petrolia State Station, situated near the coast south of Eureka, and the more inland Dinsmore Station typically register events above magnitude 2.0 on their seismographs, with signals appearing on both stations during significant activity. Despite this, some quakes remain unacknowledged by reporting agencies, fueling speculation about the completeness of earthquake data. In Texas, the earth continues to shake within the oil fields. A magnitude 4.2 earthquake, initially recorded as 4.3, was reported in the western desert region, an area characterized by a dense network of oil pads and wastewater disposal ponds. These facilities inject wastewater deep into the ground, a process strongly linked to seismicity in the area. The connection between oil extraction and induced earthquakes is well documented, and today's activity is another clear example of the earth responding to industrial processes. As the oil boom continues, so too does the likelihood of future quakes in these exploited regions. Further north, the New Madrid seismic zone remains relatively quiet with only minor tremors noted. This calm, however, contrasts with a peculiar event in the Drake Passage near the Antarctic region. A magnitude 5.3 earthquake occurred in this unusual location near a historically recognized plate boundary fracture zone. While historical data supports seismic activity in the area, the exact placement of today's event seems slightly off the expected fault line. Such anomalies often highlight the complexities of tectonic interactions in less studied regions. Meanwhile, the South Sandwich Trench remains tranquil with no significant seismic events reported along this subduction zone. Across the globe, the interconnected dance of tectonic plates continues to reveal its mysteries, reminding us of the forces shaping our planet. Seismic activity continues to unfold across various regions with notable developments along the Peru-Chile Trench. While no significant events have been recorded, smaller tremors reflect ongoing tectonic movement in this area. The Atlantic Ocean saw earlier activity, including a magnitude 5.0 and 4.7, indicating moderate seismic unrest. Meanwhile, the Ethiopian Rift boundary remains a focal point of interest due to its heightened activity. Recent observations suggest an uptick in surface changes, including fractures and geyser-like emissions of mud and water, signaling increased geothermal activity beneath the area. These phenomena align with nearly 100 recorded earthquakes in the region, including several unreported smaller quakes, likely around magnitude 3.0. Seismographic data west of the rift boundary confirms a series of tremors, including multiple magnitude 4.0 earthquakes. The patterns suggest that this tectonically active region is experiencing renewed strain with the possibility of further seismic events. Elsewhere, Hawaii remains relatively quiet with no significant activity reported. New Zealand is similarly calm, though minor clustering persists around Vanuatu and the Indonesian archipelago, consistent with typical seismic activity in these zones. The Philippines also displays moderate activity characteristic of its tectonic environment. In Nepal, the aftermath of the recent magnitude 7.1 earthquake, the strongest quake to date in 2025, continues to be monitored closely. While seismic activity has shifted slightly north of the plate boundary, this transfer of strain is consistent with expected tectonic behavior in the region. The increased pressure near the Mount Everest area suggests the potential for additional significant events. This region, shaped by immense tectonic forces, remains a critical area of focus as scientists assess the evolving seismic landscape. Earthquake activity has been relatively moderate, with some movement observed along the Middle America Trench and the northernmost segment of the Cascadia Subduction Zone. A magnitude 3.1 tremor was recorded in Cascadia, though it appears unreported on certain models, likely being catalogued by the European Mediterranean Seismological Center. These small tremors reflect the constant tectonic adjustments occurring in these regions. Meanwhile, space weather activity has seen a significant development. After more than a month offline due to server flooding at Stanford University, the Solar Dynamics Observatory, SDO, imagery is back online, providing crucial data on solar activity. This includes detailed views of sunspot complexity and ultraviolet imagery of the sun. Observations indicate some reorganization in active region 3947, which is undergoing changes in its magnetic structure. While its complexity has diminished, a lingering portion of the region still holds a slight potential for flaring. Current probabilities suggest a 15% chance for X-class flares, 60% for M-class flares, and near certainty for smaller C-class flares. However, no significant solar storms are forecasted for the near future. Now let's look back at what happened during the recent 7.0 Cape Mendocino earthquake last December. Did it set off aftershocks along the San Andreas Fault? On December 5th at 10:44 a.m. local time, 1644 UTC, a powerful magnitude 7.0 earthquake struck offshore Northern California, approximately 100 kilometers, 60 miles, west of Ferndale, a region that previously experienced a magnitude 6.4 earthquake in 2022. The U.S. Geological Survey, USGS, reported that this strike-slip event occurred at a depth of around 10 kilometers, 6 miles, a characteristic that heightened its potential impact. Initially assessed as a magnitude 7.3 event, the quake's intensity prompted the National Weather Service to issue a tsunami warning for parts of coastal Oregon and California communities from Davenport, California, near Santa Cruz to the Oregon coastline. The region was placed on high alert. However, as more data was analyzed, the magnitude was revised to 7.0, and the warning was lifted within an hour when no destructive tsunami materialized. While the tsunami warning may have startled residents, the earthquake itself was not unexpected. This stretch of Northern California lies within one of the most seismically active zones in the United States, a region shaped by complex tectonic interactions. Early analyses have also hinted at dynamic triggering, a process where seismic waves from a primary quake can activate distant faults, potentially setting the stage for further seismic activity. Near the heart of Northern California's seismic activity lies the Mendocino Triple Junction, a dynamic meeting point where three major tectonic plates, the Pacific, Juan de Fuca, and North American, collide in a relentless geological struggle. This convergence creates a tangled network of faults that marks one of the most geologically complex and active regions in the world. The San Andreas Fault, the infamous boundary dividing the Pacific and North American plates, extends northwest through California before abruptly turning to merge with the Mendocino Fault. This transform fault, spanning 175 kilometers, 108 miles, westward, serves as the boundary between the Pacific Plate to the south and the Juan de Fuca Plate to the north. To the north of this junction lies the Cascadia Subduction Zone, a vast and enigmatic fault system where the Juan de Fuca Plate dives beneath the North American Plate. Cascadia is notorious for generating massive earthquakes every few centuries, though much about its rupture patterns remains a subject of intense scientific inquiry. At the Mendocino Triple Junction itself, the immense forces between these converging plates lead to constant deformation, fracturing, and frequent seismic activity. Since 1980, this volatile zone has been rocked by 6 earthquakes of magnitude 7.0 or greater, including the recent magnitude 7.0 event. For context, the devastating Loma Prieta earthquake of 1989, which wreaked havoc in the San Francisco Bay Area, measured slightly less at magnitude 6.9. Preliminary aftershocks and seismic data indicate that the most recent quake likely originated along the Mendocino Fault, a testament to the region's ceaseless tectonic activity. A seismic gap is a portion of an active fault where significant earthquakes have been notably absent, contrasting with surrounding segments that have experienced major seismic events. Along the Mendocino Fault, experts had identified such a gap between a magnitude 7.0 earthquake in 1994 and a magnitude 6.1 event in 1983. The aftershock pattern of the December 2024 earthquake indicates that the main rupture occurred within this previously identified gap. However, aftershocks extended beyond its boundaries, reaching toward the San Andreas Fault and hinting at a possible transfer of stress to adjacent fault segments. Although the epicenter was located approximately 50 kilometers offshore, the rupture's propagation eastward brought aftershocks dangerously close to the coastline, with some within mere kilometers of populated areas. This eastward spread of seismic activity underscores the complex dynamics of the fault system. The earthquake, with its large magnitude and shallow depth, reverberated across a vast region, shaking areas as far north as Salem, Oregon, and throughout Northern California. Residents from the San Francisco Bay Area to the Central Valley reported feeling the tremors. According to experts, Cape Mendocino experienced the most intense ground shaking during the eastward propagating rupture of the recent earthquake, with seismic sensors recording acceleration at approximately 0.55 g, equivalent to half the force of gravity. To put this into perspective, this level of force mirrors the sensation of sudden braking in a car. In surrounding areas, both instruments and individuals reported significantly lighter shaking, underscoring the localized intensity near the epicenter. Cape Mendocino holds the distinction of being the most seismically vulnerable location in California, with forecasts suggesting it has the highest likelihood of experiencing a major earthquake within any 100-year time frame. According to seismic models, a magnitude 7.2 earthquake has a 1% annual probability in this region. While this may sound like a rare occurrence, the cumulative odds grow strikingly significant over time, reaching 55% within an average human lifespan of 80 years. Historical records reinforce the region's volatile nature, with magnitude 7.0 to 7.2 or greater earthquakes striking in 1922, 1980, 1992, and 2005. Numerous other tremors have approached this magnitude, further highlighting the area's geological instability. Cape Mendocino's seismic history serves as a sobering reminder of the persistent tectonic forces shaping the region and the enduring risks they pose. So, what is the impact on the San Andreas and Cascadia faults? The catastrophic 1906 San Francisco earthquake tore through 477 kilometers, 296 miles, of the San Andreas Fault, stretching from San Juan Bautista in the southeast to the Mendocino Triple Junction in the north. In light of the recent December 5th earthquake, an important question emerges. How much stress has been transferred to the northernmost San Andreas Fault? Furthermore, given that the Cascadia Subduction zone begins at this junction, an area capable of unleashing colossal megathrust earthquakes, scientists are also examining whether stress has been transmitted to this volatile subduction zone. In the week leading up to the magnitude 7.0 Cape Mendocino earthquake, most of the Mendocino Fault remained eerily quiet with no notable seismic activity. However, two foreshocks broke the silence just hours before the main event. A magnitude 4.4 tremor at 11:36 Universal Time coordinated on December 4th, and a magnitude 4.2 at 13:10 Universal Time coordinated. These smaller quakes likely signaled the imminent release of stress along the fault. Following the main shock, aftershocks clustered densely around the epicenter along the Mendocino Fault. Seismic activity radiated both eastward and southward, with about 15 aftershocks occurring well beyond the primary rupture zone. Notably, these aftershocks formed patterns that extended along the northernmost section of the San Andreas Fault and the nearby Whale Gulch Bear Harbor Fault Zone, situated just 5 kilometers inland where the Mendocino and San Andreas faults intersect. Using the USGS source model of the main shock combined with focal mechanisms from aftershocks and earlier seismic events, researchers have calculated that the northernmost segment of the San Andreas Fault was pushed approximately 0.25 bar closer to failure by the magnitude 7.0 earthquake. This stress adjustment aligns with observed aftershocks occurring near the fault's northern tip. However, uncertainty remains about whether this segment last ruptured during the infamous 1906 earthquake, leaving a slip deficit of around 3 m, or in a much earlier event, which would suggest a deficit of at least 6 m. Similarly, the southernmost section of the Cascadia Subduction zone experienced a comparable 0.25 bar increase in stress, though over a more limited area. To further explore stress transfer, scientists examined the focal mechanisms, represented by beach balls, of earthquakes in the region since 1976. These mechanisms reveal the orientation of faults affected by the main shock, with red indicating increased likelihood of slip and blue showing inhibition. Along the Mendocino Fault and the northern San Andreas, beach balls turned red, suggesting stress promotion. However, the absence of thrust mechanisms on the southern Cascadia megathrust makes the effect there less conclusive. According to experts, the interplay between the recent magnitude 7.0 earthquake and earlier seismic events offers intriguing insights. First, the magnitude 6.4 earthquake in 2022 did not bring the magnitude 7.0 epicenter closer to failure, indicating no straightforward chain reaction between the two events. However, both quakes contributed to a cumulative stress increase of 0.25 bar on the northwest tip of the San Andreas Fault. This stress has significantly affected a 40 kilometers, 25 miles, stretch where the San Andreas merges into the Mendocino Fault, now 0.25 to 0.5 bar closer to failure than before 2022. Despite this increase, the stress levels do not currently point to an imminent rupture along the San Andreas Fault. Interestingly, experts found that the magnitude 6.4 event also reduced stress by 0.25 bar on the onshore section of the northern San Andreas Fault.